We've just talked about equilibrium, and now we're going to talk about the subject of thermodynamics, the science of energy transfer. And this is sort of the next step beyond thinking just about the heat of reaction or the change in enthalpy of reaction, as we've already talked about. And what we're interested now is how to determine when a process or whether a process will be spontaneous or not, which means will it occur without external influence, and we will understand that's why a stretched rubber band, which I have right here, will spontaneously contract. And we'll talk more about that. From chapter 14, when we were talking about equilibrium, a chemical reaction that occurs in the forward direction is a spontaneous process, or at least when it has a large K value, Kc, Kp, it certainly has a very, very good likelihood. Remember, our for sure test is to say Qc less than Kc, which is also, so will a reaction happen in the forward direction? Yes, if Qc is less than Kc. Now, so in light of that, is this a spontaneous process? If we have the concentrations given here, we have Kc given, and now let's calculate Qc. Qc is going to be the same expression as Kc, except for just any given concentrations. So we have our concentration of carbon dioxide. H2O is a liquid, so it doesn't show up in this reaction, over our concentration of our reactant, carbonic acid. Plugging in our numbers, 0.01 molar over 1.00 molar. We just get 0.01 for our Qc, which is less than our Kc. Yes, this is a spontaneous process. We could also say it's a spontaneous reaction. That's the process that's occurring. Yes, this reaction will occur in the forward direction. All equivalence ways of saying the same thing. Okay. Now, the chapter 15 definition, when a process is spontaneous, is a process that lowers the free energy of the system. And we've talked about how equilibrium was always going to the lowest energy state. Now we're going to add this term free energy, and over the course of the contents of this chapter we're going to talk a lot about what free energy is. So nature is lazy, which means that nature and therefore chemical reactions always move, or nature, chemical reactions, everything, etc., always moves to the lowest free energy state. And that's where equilibrium was taking us. That's where all reactions are going. That's where this pen goes when I drop it. So, and now I want to say a couple words about spontaneous versus reaction rate. So we will always determine whether a process is spontaneous first. Because if it's not going to happen, if it's not spontaneous, then you can never even worry about what the reaction rate is. And so far we have two methods of determining if a process is spontaneous. Or we have one method so far, but we're going to talk about the second method this chapter, and then we'll talk about the third method in the following chapter. So let's just go with all three methods here. So one QC versus KC. 2 is going to be, well, what we'll see is delta G, where delta G is our free energy that we're going to be talking about, or a change in free energy, has to be less than 0. And in our third chapter, which will be about electrochemistry, E will have to be greater than 0. Anyway, we're going through 3 methods to talk about, will a process occur? Is the process spontaneous? Those are 2 ways of saying the same thing. Reaction rate just says, once we know a process is spontaneous, how fast does it occur? Once we know that a process is spontaneous, how fast does it occur? And we talked about kinetics first. Now we're going to talk about, we've talked about QC versus KC. And really, just to get philosophical for a minute here. So it's easy to measure concentrations of gases and aqueous species. And so when we think about why we're using these different methods to determine if a process is spontaneous, it's because it's the easiest way to do it, typically. So QC versus KC is a way to do it in terms of concentrations. Free energy is, or the change in free energy is going to be a way that we're going to use for reactions that typically involve large changes in energy, measurable changes in energy. And E is going to be a voltage for an electrochemical cell, and that will be easiest to measure for the reactions when we talk about batteries and things like that. Now, on our way to determining what this thing called free energy is, spontaneous reactions tend to do 2 things. First, they disperse energy. And they disperse energy, so for exothermic reactions, energy is dispersed to from the system to the surroundings. Energy then takes up a larger place, and so exothermic reactions tend to be spontaneous. And exothermic reactions, of course, mean reactions for which delta H reaction is less than 0, and heat is produced or given off. By the reaction. And the reaction, and everything we do in this course is the system. But that's not the be-all, end-all of spontaneity. That's going to be the change in free energy. That's where we're going. This is just a tendency. Now, spontaneous reactions also tend to disperse matter, and what we mean by that is just like energy, energy is dispersed, so matter is dispersed. Matter is dispersed when matter is spread out. Okay, and that can mean, so something as simple as taking matter in one bulb and allowing it to expand into a second bulb. And so let's watch a little video about that.
Gas in the filled flask will move spontaneously to the empty flask by its molecular motions. Eventually, the distribution of molecules will be even throughout the flasks. The final state, in which the matter is more dispersed, is much more probable than the initial undispersed state.
So matter is dispersed when matter is spread out. It can expand into a new space. Or let's say this, expand into a larger volume. It can react to into more pieces, react into more particles. And for example, when it goes from something like, that's a gas, dinitrogen tetroxide to nitrogen dioxide, it is reacting and breaking into more particles. So that's another example. It is, so another way is it can expand, or it can distribute into more positions, distribute. And it can distribute into more energy levels. And dispersal of matter is measured by entropy. And entropy is typically thought of as the disorder of things, and there's a lot of ways in which that works. It's, I think, a better way to think about it in terms of dispersal of matter, matter being more spread out. I guess the one other thing I can say, dispersal of matter, matter is more random. And I guess I should say more randomly positioned. And what we will see as well is that the more, this is a take-home message, so I'll write in red, the more the more random it is, or I guess, so more random positions will be associated with, or more dispersed matter will be associated with more ways of, or a higher probability of occurring. So matter is more randomly distributed. I don't know, let's see if that comes out in the things that we're going to be doing. Now it's time for a demo. The demo is the contracting of a rubber band. If you've got a rubber band, please use it. Oop. But here's what this looks like. Take a rubber band and stretch it. And you know that if you let go of this rubber band, it is going to snap back. So a contracting rubber band is a spontaneous process. Now, after having it stretched in approximately the same position, take the rubber band and place it against your upper lip, and then allow it to contract while still holding onto it. And what you should feel is that the contracting rubber band felt cooler, lower temperature. And that's why you place it against your upper lip, is your upper lip is actually pretty sensitive. So, and actually, if you do the opposite, if you take a non-spontaneous process and you go like this, you should actually be able to feel the opposite, that heat is given off. And if it's one thing we've talked about, it's that when you reverse a process, it changes the sign of the energy. So either way that you can do that, it's fine. We're going to focus on the demo of the contracting rubber band. And that's because for the contracting rubber band, it's spontaneous. And so let's see. So the demo was for a contracting rubber band. Contracting rubber band is spontaneous. My little brother and sister can tell you that because they used to shoot them at me. Anyway, so the demo is stretch rubber band. Stretch rubber band. Hold for 30 seconds. Place rubber band against upper lip. Allow rubber band to contract. Feel the cool. These are ditto marks. Oh, you can't even see what I'm writing. I'm sorry. I'm writing all this. Is spontaneous. Stretch rubber band. Hold for 30 seconds. Place rubber band against upper lip. Allow rubber band to contract. And feel the coolness. And the reason we're doing this is to show you that in a simple non-chemical way, or typically non-chemical way, more of a physics way, that conclusion, an endothermic process is spontaneous because the process is endothermic because it's taking in energy. That's why it feels cool. An endothermic process is spontaneous, even though it is not dispersing energy, which is a tendency that we just talked about as to things that happen. So why? And the answer is, of course, that a contracting rubber band disperses matter. So I guess the question would be, why? Bill says why a contracting rubber band disperses matter. And I guess I should say why. Who, what? So who are these people that care about why a rubber band contracts? And why does it matter? And what is matter? Well, now let's show you what this means. So if you stretch a rubber band, you actually take the different strands that are in it, and they're actually more or less carbon chains. And they look sort of like this. And we've talked about skeletal or line bond structures, so that's pretty much what they are. And what we will see is that when you stretch them, they are very well ordered, and there are very few ways in which they can be. So this is a stretched rubber band. And there are very few positions for each of the atoms. And actually it should go out in this way too. And then a contracted rubber band is, so these move much closer together, And the rubber band pieces look more or less all disordered, and there's lots of ways in which they can tangle and untangle. So many positions, very tangled. And even though it's closer together, because they have many positions, many configurations, and are all jumbled up, all disordered, this is the more dispersed which is again hard to think about, but it is true. And that's the demo of the rubber band.